Very good morning to Mr. Fauzi. Today we're going to present on phenol production for chemical process design and optimization. So my name is Niu Xiang. Okay, these are my group mates. Okay, what is sustainability? Sustainability is the ability to sustain itself and move as a whole with social, economic, and environmental aspect. So natural resources are limited, so we should conserve in long-term priorities. Sustainable design of industrial processes is the design activity contribute to economic growth, environmental protection, and social progression for the current generation without compromising the potential of future generation to have ecosystem that meet their needs. So next, what is environmental sustainability? Environmental sustainability is the ability to make decision and action by protecting natural resources and preserving the environment to support human life. So all phenol products, as we all know, are currently derived from petroleum, which is dwelling resources and require intensive energy resources. So acetophenone produced during the production contributes to the detrimental hazardous air pollution. So there might have a possible increment in respiratory infection such as asthma, pneumonia. So heat integration and process optimization are performed to reduce energy consumption and emission for the processes. So next I'm gonna brief out the general description of processes. So acetone as a side product is removed as overhead in the first column, purified by distillation. For bottom product is distilled in vacuum column to produce unreacted cumin and byproduct of methylstyrene as overhead. So unreacted impure cumin and methylstyrene need to recycle back for further purification in order to achieve higher purity and yield. So recovery of unreacted feed and exothermic heat produced must be done so that plant can be profitable without compromising the sustainability aspect. So acetophenone and acetone as side product are prepared to sell or for other usage. So all waste generation follows environmental quality. So for economic sustainability is the application of numerous strategies to employ existing resources with a responsible and beneficial balance in long run term. So there are strong demands for derivative of biphenol A and phenolic resin. So long-term profitability is ensured for growth in economic aspect. So next is the world consumption for phenol in 2015. As we can see, Western Europe, United States, and China are the three largest countries that consume phenol. So next slide will be supply and demand of phenol. So as we can see, as the year increases, production and consumption of phenol actually increases. So for the capacity of phenol in global market, from 2009 to 2015, the supply quantity actually increased from 8.58 million tons per year to 11.37 million tons per year. So for next, we're going to discuss our social sustainability for cohesion of society with the ability to work properly to maintain common goal. So handling and phenol product must be implemented. Health and well-being education also must meet in any workplace. So suitable location for plant actually provide optimal relationship among manufacturing process. So actually more job opportunity will be introduced as the demand of phenol increases. Thank you.
Hi, my name is Anusia. So the first synthesis step is to select the reaction part for the production of phenol. In cumin peroxidation process, cumin reacts with oxygen to produce phenol and acetone. This process has high yield of products and valuable byproducts are formed. A large amount of byproduct is formed also. In toluene two-stage oxidation process, toluene is oxidized in two stages to produce phenol, water, and carbon dioxide. This process generates less waste, but it's an energy-intensive process. In DOE process, benzene in the presence of chlorine and sodium hydroxide forms phenol, sodium chloride, and water. This process has high product yield, but HCl formed as an intermediate product can corrode the unit operations. By comparing the gross profits, cumin peroxidation process with the highest profit is selected as the best process. The distribution of chemicals was performed to match the flow rates of the sources and sink. It is targeted to produce about 90 million kg per hour of phenol yearly. By assuming that the plant operates 330 days per year and 24 hours per day, the hourly production of phenol is about 11,370 kg per hour. By stoichiometric calculation, cumene about 15,000 kg per hour and oxygen about 3,900 kg per hour can produce 7,017 kg per hour of acetone and 11,400 kg per hour of phenol. But oxidation has a conversion of 25% and cleavage reaction has a conversion of 100%. So a recycled stream with about 55,000 kg per hour is required to return back the unreacted cumene. It is advised to introduce the feed streams in excess because even if there is some material loss due to plugging in the pipelines, the targeted amount can be produced. Another option is to introduce the feed stream in stoichiometric amounts. But if there is any loss of materials, the targeted amount cannot be produced. Hence, option 1 is selected. The effluent leaving the reactor consists of phenol, acetone, cumene, and AMS formed in the side products and the side reactions. Phenol has low purity, thus, to eliminate the composition difference, a series of distillation columns are used. The components separated here are based on boiling points in which the component with the lowest boiling point is separated first. Another option is to use a single column with side streams. But the components separated here have low purity and hence cannot be sold. Thus, option 1 is selected. Here, the oxidation occurs at a higher temperature and pressure compared to the cleavage reaction. Thus, the changes in temperature and pressure is achieved by placing a cooler. The AMS conversion occurs at a lower temperature but higher pressure compared to the parameter of the stream leaving the distillation column. Hence, the changes here are achieved by first cooling the stream and then pumping it. Another option is to compress the stream first and then cool it. However, this is not possible since the stream leaving the distillation column consists of partial vapor and liquid and it cannot be compressed. Thus, option 1 is selected. In task integration, the unit operations involved are placed in sequence to complete the process flow. The recycled stream and feed streams are introduced to the mixer before it enters the reactor. Another option is to introduce the streams separately to the reactor, but this is not possible because they have different flow rates. Hence, option 1 is selected. This is the synthesis steps in the synthesis tree in which the bolded line shows the selected part for the production of phenol. And this is the initial process flow diagram showing the processes involved in the production of phenol by the cumene peroxidation process. Thank you.
Hi, my name is Ahalya and I'll be discussing about the separation train synthesis. The sequence in which the products are separated is very important for several reasons. This can be determined from 4 methods, which is marginal vapor flow, minimum vapor flow, heuristic, as well as annualized cost. We will be discussing about minimum vapor flow as well as heuristic. For the production of phenols, 4 products can be distilled from 3 distillation columns, which are acetone, cumene, alpha-metylstyrene, and phenol. For these 4 products, it can be approached in 5 different sequences as shown in the screen. For sequence 1, acetone was distilled off as the distillate from the first distillation column. This is because acetone was the light key component. From the second distillation column, cumene was removed as the distillate stream. In the final distillation column, methylstyrene was the light key component and this was removed as the distillate stream. And finally, phenol, which is the heavy key component, was removed as the bottom product. All other sequences were also developed based on the light and heavy key component concept. The calculations were performed based on these 2 formulas, which is where R min is the minimum reflux ratio and D is the molar flow of the distillate. The total vapor flow was calculated by summing up the vapor flow of each distillation column. Since we used the shortcut distillation column, the minimum reflux ratio was determined from the parameter step of the shortcut distillation column, and the molar flow of the distillate was determined from the distillate stream. Based on this table, it can be seen that sequence 1 had the lowest vapor flow, followed by sequence 2, 5, 4, and finally sequence 3. Having the lowest vapor flow is important so that the cost incurred by the company will also be reduced. So it can be seen that sequence 1 is the best sequence. The next method is the heuristic method. The heuristic method gives a guideline on how to separate components effectively. We used heuristic 1 to remove flammable acetone to prevent any possible explosions from occurring. We use heuristic 3 to remove the most plentiful component, which was cumin. After removing acetone, cumin was produced in abundance, and therefore this was removed from the second distillation column. Then we used heuristic 2, as this followed the direct sequence approach in which the components were separated based on the boiling point from the least to the most. Heuristic 4, which is similar to heuristic 2, was used to separate the components based on volatility. The most volatile component was removed first. Finally, we used heuristic 5 to remove the highest purity product last. Phenol, which was the main product, had the highest purity, and therefore this product was removed last. From this, it can be seen that sequence 1 met 5 out of 6 heuristic and therefore is the best sequence. This is the revised version of the PFT based on the separation train synthesis. We can see that we have used sequence 1 for the distillation columns, as this is the best sequence. Thank you.
My name is Ong Guang Jian. I would like to present about the process optimization process of production of phenol. So after production of phenol, there will be an optimization process, which is you need to maximize your production of phenol by increasing the mass flow rate, or you can increase the molar flow rate by optimize the utility cost of the process. So in the economic side of view, you need to increase to maximize your profit of the process. So this is our objective function for this optimization, which is maximum annual profit, and we have 3 constraints. So 3 constraints. The first constraint is about AMS conversion, which is alpha methylstyrene. The conversion of AMS must be always higher than 2%, which is if you increase the percentage conversion, so more AMS will then be produced for the recycling process at the simulation, so it will increase the production of phenol. So for the second constraint is about the molar flow of cumin hydroperoxide, CHP, which is located at stream 5 in the simulation process right after the plug flow reactor. So if you set the molar flow rate of CHP in the stream which is less than 12 kmol per hour, so the CHP is being converted to the desired product, and it will then increase the percentage of conversion of phenol. So the first and second constraint is all about increasing the production of phenol. So the third constraint is about the mass flow rate of phenol. So phenol must be the mass flow rate of phenol must be larger than 7,200 kg per hour. So the production of mass flow rate in the distillation column must not less than 7,200 kg per hour, which is our third constraint. So after the constraint, we can look at our optimization utility stream. So before optimization, we have 13 stream. Comparing to the utility stream after optimization, there will be also 13 stream. But the difference is that more heat, more condenser and more reboiler power will be used after optimization process, because if you increase some of the reboiler and condenser, more phenol product will be produced, although the cost will be high. Comparing to the before optimization, as you can see, the annual profit of before optimization will be $9.9 million profit, which is very low compared to the after optimization, which is $16 million profit annually. So the revenue for before optimization is approximately $187 million revenue, comparing to the optimization after optimization, which is $221 million. So it is quite such difference, which gives us a more higher profit after optimization. So last but not least is the second is the optimizer in the simulation process, which is, as you can see in the slide, before we have optimization, there will be the current value that we set for cumin for mass flow rate is about 300 kg per hour, and for air is approximately 750 kg per hour. But as you can see, after optimizer, the cumin mass flow rate for cumin is decreased to 256.7 kg per hour, and the air mass flow rate, mole flow rate will be decreases to 600 kilomole per hour. So this will increase our maximum profit of phenol by decreasing the utility costs of the process.
My name is Chiu Zhihong, and I'll be presenting about the heat integration part. As a topological optimization, heat integration is carried out to design an optimal heat exchanger network that requires the minimum amount of utilities and heat exchangers. So there are two steps involved in heat integration. First, problem table algorithm, also known as PTA, is used to obtain the pinch temperature and energy targets for heat exchanger network. PTA is chosen in this case due to its higher accuracy and rapid to obtain the result compared to composite curves. Then based on the pinch temperature obtained, an optimum heat exchanger network is designed by using the pinch design method for maximum heat recovery. As in our case study, there are 7 hot streams and 5 cold streams. And while assuming delta T min, which is the minimum temperature difference between hot and cold streams, is 10 degrees Celsius, since the temperature delta T min of range of 10 to 20 degrees Celsius is suitable for petrochemical industry, which is phenol in our case study. The first step of PTA is to set up the shifted temperature intervals in order to make the shifted composite curves to touch at the pinch point. So this can be done by subtracting half of delta T min for hot stream to make it colder, and adding half of delta T min to cold stream to make it hotter. Then, based on the shifted temperature intervals, the energy delta H balance is calculated by using the formula of the difference of heat capacity between the hot and cold streams times with the shifted temperature intervals. Lastly, heat cascade was performed based on the energy balance. By adding back the largest heat deficit, we can obtain the pinch point at 140.7 degrees Celsius. Hence, the pinch temperature for hot stream will be 145.7 degrees Celsius and cold stream will be 135.7 degrees Celsius. The minimum hot utility is obtained from the top of heat cascade, which is 141 megawatt, and minimum cold utility obtained from bottom of heat cascade, which is about 154 megawatt. After determining the pinch temperature from both hot and cold streams, pinch design method is used to design the heat exchanger network for maximum heat recovery. There are 2 rules applied in pinch design method. For above pinch, heat recovery is only allowed when the heat capacity of cold stream is larger or equal to the hot stream, as well as when the number of cold stream is greater than the hot streams. So this applies in an opposite way for below pinch, in which heat recovery is only allowed in below pinch when the hot heat capacity of cold stream is less than or equal to the heat capacity of hot streams. So based on the pinch design, we have found out that 3 streams of heat recovery can be obtained. So for below pinch, heat recovery can be obtained by recover heat from recycled cumin to heat up the fresh feed of cold cumin and air streams. And for above pinch, heat recovery can be obtained by using the heat from column 3 condenser to heat up the column 1 reboiler. And based on our calculation, we found that there are 19 heat exchanger units need to be used in the heat integration. So this is the process flow diagram version 3 based on heat exchanger network to maximize the heat recovery. As a conclusion, the case study on phenol production is done by using cumin peroxidation process, as this process has the highest gross profit compared to the other 2 processes. For separation sequence, based on heuristic method and minimum vapor flow method, sequence 1 is selected as the best sequence, in which acetone is separated first, followed by cumin, AMS, and phenol. Parametric optimization was conducted to maximize the total profit for phenol productions from $9.9 million to about $60 million. And lastly, heat exchanger network is designed to maximize the heat recovery based on PTA, followed by pinch design method. As a conclusion, the objectives on separation sequence and both parametric and topological optimization of the phenol production has been achieved with satisfactory results. Thank you.